Welcome back to Topic 41, Solving Rational Equations for Algebra 2. In Part 2, we're going to focus on word problems. The first word problem that we have is Dalen and Alexa can paint a wall for a school art project in 6 hours when working together. Alexa works twice as fast as Dalen. How long would it take Alexa to paint the wall if she were working alone? So something that I've personally noticed when dealing with rational equations, and specifically word problems for solving rational equations, is that they often deal with rate, because rate can be expressed in a fraction or in a ratio. So dealing with this problem, we're dealing with the work rate for both Dalen and Alexa. Now the work rate, in this case, is the fraction of the job completed per hour. So that's where we deal with the fraction. We have the per hour. So usually what I think with these kinds of problems, the hardest part is first coming up with your equation, because it's not given to you right away. So we know that Dalen can paint a wall. We just don't know specifically how long. So we know that Dalen can paint an entire wall in X amount of hours. We don't know how long specifically, so we'll just use X as our variable. So Dalen paints one wall in X hours. Now, because the problem is focusing on what Dalen and Alexa can paint together, it says that if they were working 6 hours when working together, we know that that deals with addition. It also says that Alexa works twice as fast as Dalen. So, in the time that it takes Dalen to paint just one wall, it actually takes Alexa the same amount of time to paint 2 walls. She can paint 2 walls in that same amount of time. Because Alexa is twice as fast as Dalen. However, we also know together that they take 6 hours to paint one wall. So one wall can be completed in 6 hours. So here is our equation. Now, just like in part 1 where we were given an equation, we also need to identify what the least common denominator is. So the least common denominator here is we have to take into account our x, but we also have to take into account our 6. So the least common denominator is 6 times x, or 6x. So I'm going to rewrite my equation, but again, just to leave a little bit more space. Because we're going to multiply every single thing by that least common denominator. What we're really doing is we're multiplying both sides by that least common denominator and just distributing. But I personally, again, like to write it with every single term. It's just easier for myself to visualize. Now we're going to simplify. So our x's reduce, and also the 6's reduce in the last term. So we're left with 1 times 6, which is 6, plus 2 times 6, which is 12, equals 1 times x, which is x. So we have a linear equation. In other words, 18 is x. Now, X is referring to how long it takes Dalen to paint the wall. It takes Dalen 18 hours to paint the wall. But if Alexa works twice as fast, how long is it going to take her? So it takes Dalen 18 hours to paint the wall. So since Alexa is twice as fast, it would take her half as long to actually paint the wall. So it would take Alexa 9 hours. And that is the first word problem. Moving on to the second word problem. This one's definitely a little bit more complicated. So the second word problem reads, paddling with the current in the Charles River, Guy traveled 16 miles. Even though he paddled upstream for an hour longer than the amount of time he paddled downstream, he could only travel 6 miles against the current. In still water, Guy paddles at a rate of 5 miles per hour. What is the speed of the current in the river? Whew, this is a lot to take in. So first, we're going to, again, determine what are we actually dealing with. I mentioned before that rational equations, the word problems related to them, deal a lot with rate. So if you recall, distance equals rate times time. So another way that we could rewrite this, if I wanted to solve for just time, time is equivalent to distance divided by rate. Now I know what you're thinking. Well, the question asks us, what is the speed of the current? So doesn't that have to deal with the rate? Yes, it does. But we're actually, in our problem, given some information about the rate that we can use in our denominators. However, the problem as a whole says that it takes, even though Guy paddled upstream for an hour longer, we're dealing with this unit of time. So if we want to write our equation, we're going to do it in terms of time. But also note that time can be expressed as distance over rate. So the problem wants to know the speed of the current, so we are going to have to introduce a variable. Let's just say that C is going to be the rate of the current. Okay. So let's break it down and identify what our equation would be. Paddling with the current in the Charles River, Guy travels 16 miles. So that's our distance. Now in our problem, it says that Guy paddles at a rate of 5 miles per hour in still water. So that's going to factor into the rate portion of our fraction. It's just that when Guy is paddling with the current, he has to incorporate the rate of the current and the 5 miles per hour rate that he himself paddles. So we're going to add C here. Now our problem says that even though he paddled upstream for an hour longer than the amount of time he paddled downstream. So if he paddled upstream an hour longer than he paddled downstream, in order to make them equivalent, we would need to add 1 to the time that he paddled downstream. So it took him longer to paddle upstream, But because we're dealing with an equation and we want the equation to be balanced, we have to compensate by adding that onto the other side. So when he was paddling upstream, he paddled for 6 miles. So that's our distance. Now here we have to take into account the rate that Guy paddles, which is 5 miles per hour, and also the speed of the current. Now because he's paddling upstream, the speed of the current is going to take away from Guy's natural rate that he is paddling in the water. So we're going to be dealing with subtraction here. So let's just go through that one more time just to make sure we're all on the same page. So on the left-hand side, we know that Guy is paddling 16 miles downstream. This 5 plus c in the rate portion of our fraction is Guy's paddle rate in still water and the rate of the current. And this is because the current is working in his favor. So he normally just paddles 5 miles per hour, but because he's going downstream, he's going with the current, he's going to increase his speed. Now if we look on the other side, where we have this 5 minus c, this is Guy's paddle rate in still water minus the rate of the current. And again, it's obviously more difficult to paddle upstream. You're working against the current. So his normal rate of 5 miles per hour, the current is going to take some of that away from him to make it difficult for him to paddle, and naturally he will probably paddle slower. Now this 1 is the 1 hour. Because Guy paddles 1 hour longer downstream than upstream. And there we have it. So now that we've fully completed our equation, we're going to go about and solve it. I'm going to rewrite it on the next slide just for more space. So we have 16 over 5 plus c plus 1 equals 6 over 5 minus c. So our least common denominator that we have here is 5 plus c and 5 minus c. So I'm going to multiply that to every single term. And now I'm going to simplify. So since we have a 5 plus c and a 5 plus c, that reduces to 1. Our middle term, we'll just need to multiply that out in a second. And then our 5 minus c and our 5 minus c. So what we're left with is 16 times 5 minus c plus 1 times 5 plus c times 5 minus c equals 6 times 5 plus c. So our denominators have just simplified to 1. We can quickly multiply this. 16 times 5 is 80 minus 16c plus, now this is just a difference of squares. So we have 25 minus c squared, and that equals 30 plus 6c. So I'm going to combine like terms and then rewrite this quadratic so it's written in standard form. So we'll end up with 105, if we combine our constants, minus 16c minus c squared equals 30 plus 6c. I'm going to bring over all of my terms on the left-hand side so I can set my equation equal to 0 so I can ultimately factor and solve for c. So I'll get c squared plus 22c minus 75. If I factor that, I need two numbers that multiply together to get negative 75, but add to get positive 22. 22. I had to. Okay, so we get c plus 25 and c minus 3. Using the zero product property, we know that c can equal negative 25 or 3. Now, none of these values are extraneous in terms of looking at our denominator. But if we think realistically about our solution, we actually have a solution that would not work. So this negative 25 is extraneous because the current can't be a negative value. So that leaves us that the speed of the current must be 3 miles per hour. Thank you for watching part 2 of topic 41 for Algebra 2, Solving Rational Equations. Thank you for watching.